Hello and welcome to P2 Electricity, and this is lesson 3, and this lesson's on resistance. My name is Mr. Cooper, I'm a Director of Science with Outward Range Academies Trust. Today's lesson, you'll need some pen and paper please, and can you remove any distractions that you have. So for a starter activity, because we're looking at resistance, what things come to mind when you hear the word resistance? And you've got 60 seconds just to jot any ideas down. Okay, excellent, and stop there. Let's see what we've got. So let's have a look at some of our ideas. We've got a political resistance. We've got fitness. We use resistance bands. You've got the French resistance. All of these images imply something working against something else. In electronics, we use resistance a lot because you have a certain amount of current flowing, and you can control the amount of current flowing using resistance, or you can use resistance in order to convert electrical energy into thermal energy or kinetic energy using resistance. So in today's lesson we're going to explain the factors that affect the resistance of a component, and we're going to recall and apply the equation that links I, which is current, V, which is voltage, and R, which is resistance. So what is electrical resistance? So as the name suggests, resistance resists a current. Resistance is a very useful property that allows us to control electricity. A simple model of electricity could be like students flowing around a school, where you've got a number of students which are representing the electrons passing a point in a particular time in the school is like the current. So a lot of students passing one point is a high current. One or two students passing one point is a low current. The energy they use up in the passing of this point is the potential difference. And if we were to place a wall of jelly across a corridor, for instance, it would make it very difficult for the students to get through. This would increase the resistance. Students would slow down, which means the current decreases, and it would require a lot more effort, which means work is done by the charge on those electrons or those students. So this diagram is a good representation of how resistance works and how it affects the currents. You've got metal ions, which are positive, and you've got electrons, and the electrons are trying to move from one end of the wire to the other end of the wire. And in doing so, there are certain interactions that take place as the electron moves through the wire. It's key to note that in this diagram, the metal ions are fixed. They don't move, but they can oscillate or vibrate around a particular point, but they don't actually move down the wire. You're looking at the electron, which is the blue dot, and following its path all the way to the right hand side of the diagram. So what I'd like you to do is look at point 1, 2 and 3. Point 1, what interaction between a metal ion and an electron is the cause of the resistance? Point 2, what happens to the electron after your answer to question 1? What is the effect on the current? And point 3, what is the effect of resistance on the metal ions and the material as a whole? I'll just give you a minute just to think about some of those responses. Okay, and stop there. Let's have a look at some of your responses. So, the interaction between a metal ion and an electron is the cause of the resistance, and it's a collision. The electrons collide with the metal ions, and this collision results in an energy exchange. What happens to the electrons after your answer to question 1? What is the effect on the current? Well, the current has lost energy to the metal ion, which means that the current decreases. So the more collisions there are, the less current there is. And point 3, what is the effect of the resistance on the metal ions and the material as a whole? Well, the metal ions during these collisions gain energy, and in this particular case the material will heat up eventually. So what I'd like you to do now is watch the following demonstration, and can you write down any of the key terms that are often being used to explain what is happening in this next demonstration. Okay, so here's a great demonstration to show you resistance. What we've got is we've got a power pack, we've got an ammeter that measures the current, and we've got a really thin wire here. And what we're going to do is we're going to show you the fact that you've got electrical energy provided by the current, and that can be converted into thermal energy and a little bit of light energy. So if I turn the power pack on and increase the voltage slightly, what you should see is an increase in current, but our main focus is actually on the wire. So if I increase it a little bit more, we should see a slight movement in the wire. What I'm doing is I'm increasing the number of electrons going through the wire, which increases the number of collisions. And it's very similar to you rubbing your hands together, where you're using kinetic energy, and that kinetic energy is getting converted into thermal energy as your hands heat up. We've got electrical energy, we're increasing the number of collisions, and that's causing an increase in resistance, which eventually, and we could feel it slightly, causing an increase in thermal energy. So you can feel a slight bit of heat there, and you might be able to see a slight glowing red at that part. But if I increase it once more, we should see the majority of the wire turning red now. And just to demonstrate that we've got heat coming off, here's a polystyrene cup, and what I can do is demonstrate that it easily glides through the polystyrene cup, melting the polystyrene cup and cutting it. So there we have, we've got resistance, we've got an increased resistance, we've got an increased current, increased number of collisions, and therefore those collisions and that energy is getting converted to thermal energy as well as light energy. Thank you for listening. Excellent. So there we've had a demonstration, and key terms we use such as current, increased current, voltage, increased voltage. We've got thermal energy, we've got resistance and the increased resistance, and we've also got light energy given off. Okay, so we've used the term voltage, current and resistance. Now all these terms are linked in one equation that you'll have to know and have to be able to recall and apply in any particular exam question. So V represents volts, which is the potential difference. I is current and is measured in amps, and R is the resistance and is measured in ohms. And something called Ohm's law is something that we'll explore a little bit further down the line. But here we are, we've got a large V in this one, a tiny I and a large R. Now what we need to do is we need to explore how these quantities affect each other. So if I increase the size of voltage, how does that affect the size of I? And how does that affect the size of R? Similarly, if I increase R, how will that affect I, the current? How will resistance affect the potential difference in volts? So let's have a look at this next bit of software. Okay, so this bit of software is essentially explains the relationship between voltage, current and resistance. Here, if I increase the voltage, you'll notice that the current, I, increases a little bit, but not significant. If I reduce voltage, then I also reduces. So you could write a sentence about the relationship of increasing the voltage on how that affects the current. If I increase the resistance, you can see as R gets bigger, and then as R gets smaller, I increases, but you'll notice that if I increase R to the two extremes, highest and the lowest, you'll notice that V doesn't change, but it's a relationship with I, the current, that changes. If I reduce the resistance, you'll notice that there's a large current that's allowed to flow around the circuit. As I increase the resistance, you'll notice that the current gets smaller and smaller. However, the voltage stays the same. So you may need to use the terms proportional or inversely proportional in order to describe that relationship. Can you make notes in your book as to the relationship between V, I and R? So in order to find out the resistance of a circuit, we need voltage and we need current. R is volts divided by current, or R is potential difference divided by current. And resistance can be calculated by measuring the current and the potential difference. So, how do you measure the current and potential difference? I'm going to give you 1 minute to try and think of a circuit that involves something that measures current and something that measures and provides a potential difference. So how would you measure the current and potential difference of any particular resistor? Can you draw or sketch a circuit that you'd use? Okay, so our sketch of this circuit should look something like this, where you've got an ammeter, symbol A, and you've got a voltmeter with the V. Now, using this diagram, can you use appropriate scientific language and describe how current and potential difference are measured. Okay, let's see how we've got on. So we should have stated that the ammeter is used to measure the current, and the ammeter is in series with the resistor and the cell. And we've also got a voltmeter which is used to measure the potential difference, and that's in parallel or across the cell. Okay, so here's the circuit diagram. If we then add in the components, we've got the voltmeter, the ammeter, the cell, and the resistor, which is that green item at the bottom of the screen that's connected between the two crocodile clips. If we then add in the wires, we'll have a diagram similar to this. So as you can see, the voltmeter measuring the volts is parallel to the cell, and the ammeter is in series with the cell. So we can take both readings of the potential difference from the voltmeter and readings of current from the ammeter. Okay, with the mindset of practice makes progress, let's have a look at some exam style questions. So, question 1. Calculate the resistance of the bulb. We've got ammeter there reading at 2 amps, and we've got a voltmeter reading at 3 amps. We know we've got the equation V equals IR, which you can apply. So I'll give you 1 minute to attempt that question. Okay, let's see how we've got on. So, V equals IR is the equation that we've been given. We know we've got 3 volts reading from the voltmeter. We've got a current reading of 2 amps, and we can put that into the equation. We'll then need to rearrange the equation in order to get R on its own, which will give you R equals V over I, which is 3 volts divided by 2 amps, which results in 1.5 ohms. Remembering the unit of resistance is ohms. Okay, let's have a look at question 2. So, correctly describe how an ammeter could be connected within this circuit. A diagram could be enough. So you could draw the diagram and draw where the ammeter could be connected, or you could write a sentence. The second part of this question is calculate the current through a resistor. So there we've got the resistor of 12 ohms and we've got a voltage of 6 volts. So I'll give you 1 minute to attempt that question. Okay, let's see how we got on. So, correctly describe how an ammeter could be connected. So in this particular diagram, and in all circuits, we should have the ammeter connected in series, measuring the current going through the circuit. Calculate the current through the resistor. So we can calculate the current. We know V equals IR. We've got the voltage at 6 volts. We don't know the current, but we know that the resistance is 12 ohms. We need to rearrange that equation to make I the subject. So it's I equals V divided by R, which is 6 divided by 12, which is 0.5 amps. Question number 3. Calculate the resistance produced by the resistor. So we've got volts there and we've got a current reading of 0.3 amps. So I'll give you a minute to attempt that question. Okay, let's see how we've got on. So we know the equation V equals IR. We've got voltage and we've got current, which leaves R as the unknown. We'll need to rearrange the equation in order to make R the subject. R equals V divided by I, which is 6 divided by 0.3, which gives us a resistance of 20 ohms. Okay, question 4 then. So, if the resistance of the resistor is halved, what would be the current? Now, we recognise this diagram because it's from question 3, so you could probably work it out mathematically, or you could give a general pattern of what you think would happen. But you've got 60 seconds to complete this question. Okay, so the general pattern would be if you're decreasing the resistance, so if the resistance of the resistor is halved, you're decreasing the resistance, which means that you're allowing more current to flow through the circuit. Now, from the previous question, we know what the resistance would be. So we've got 6 volts and we've got 0.3 amps, but we're trying to work out what's going to happen to that ampage when we decrease the resistance. So we've got 6 volts, and from our previous answer we knew we had 20 ohms. We've now halved that into 10 ohms. We rearrange the equation in order to make I the subject, so I equals V divided by R, 6 divided by 10 equals 0.6 amps. So if you halve the resistance, you're then going to double the current. So final question then, correctly describe how a voltmeter could be connected. A diagram could be enough. So you're working out how a voltmeter could be connected in this diagram in order to read the potential difference. Also, can you calculate the current going through this circuit? So you've now got a minute in order to complete that question. Okay, so a voltmeter is always connected across a component. So a voltmeter would be connected in parallel to the cell for this particular circuit. In order to calculate the current through this circuit, use the same equation, but you've got 3 resistors there. Now in a series circuit, you need to add up the 3 resistors in order to get the total resistance. So we've got 12 volts. We don't know what the current is at this stage, but we do know that we've got 3 resistors that we need to add up in order to get the sum of the resistance. We rearrange the equation in order to make I the subject. I equals V divided by R, which is 12 divided by 1500 ohms, which gives a current reading of 0.008 amps. So that concludes our introduction to resistance. Thank you very much for listening, and I look forward to presenting to you in lesson 4.